Hello, my name is Herve Nyemeck. I am a senior at School Without Walls Senior High School in Washington, D.C., and the title of my project is Improving the Efficiency of Hydrogen Internal Combustion Engines with the Intention of Commercialization. What I found in my project is that while hydrogen gas is a promising alternative to gasoline, gasoline is still more efficient and viable than hydrogen in all factors except one. Hydrogen gas is a proposed alternative fuel for traditional gasoline engines. Hydrogen internal combustion engines, the engine concept for hydrogen fuel, is based on the traditional combustion engine design. The BMW Hydrogen 7, for example, is a vehicle that uses the HICE engine design. In my experiment, I looked at the efficiency of hydrogen gas and compared it to methane gas, another alternative fuel source, and isooctane, the main component within gasoline. I tested efficiency for hydrogen, methane, and isooctane by creating a combustion simulation. I used OpenFOAM, a computational fluid dynamics software, and its ChemFOAM solver to simulate the combustion of all of these fuels. ChemFOAM allowed me to look at each step of the combustion reaction for each fuel. I went into my combustion folder and further into that my ChemFOAM folder and looked at the zeros, which allowed me to change the initial properties of my fuel, which I changed to 101,325 pascals for pressure and 1,000 Kelvin for temperature. In the terminal emulator, I set the directory to reflect which species I was using. In the combustion folder in ChemFOAM, I highlighted hydrogen gas as the folder that I was using so that when I ran the test, it would use hydrogen gas. I ran the command /allrun, which produces a log, which you can see here. The log needs to be removed after each test in order to create a new log. This is a log that's produced, log.chemfoam. Within this, you can see each step of the combustion reaction, the creating of the cell mesh, the starting of the time loop, and the increase in temperature and decrease in mass of the fuel. There are multiple steps within the 0.001 second interval, with an overall clock time of 1 second. Then I used ParaView, which is the post-processor for OpenFOAM, and this allowed me to visualize the reaction. In the bottom right is where the mesh is held. Since I already had a ParaView window open, I just opened that one and looked at the end step for the combustion reaction. I set it so it looped because the reaction only proceeds for 0.001 seconds. And if I were to only play it once, it would only last for a second on the screen, as you can see here. You can see the dispersal of the fuel within the entire mesh. OpenFOAM also creates a graph of the reaction. You can see here is OF versus ChemKin2. It relates it to the prospective values from ChemKin, which is another combustion solver. These graphs are visual representations of the fuel during the combustion time step and show the increase in temperature and dispersal of the substance. I calculated for percent yield and found that based on my percent yield test, isooctane is more efficient than both methane and hydrogen. As you can see in this figure, isooctane has a percent yield of 2.128 times 10 to the negative 13% at 50 atmospheres. And here, at 1 atmosphere, hydrogen had a percent yield of 1.006%. And in this figure, at 14 atmospheres, methane had a percent yield of 1.019 times 10 to the negative 11%. Since combustion is more thermodynamically efficient at higher pressures, this finding is supported. Despite this, the enthalpy of reaction for hydrogen was higher than isooctane, with hydrogen requiring less activation energy for combustion. While hydrogen is a great fuel source and has the potential to replace gasoline and other alternative fuel sources, more research is required in order to increase its efficiency in terms of percent yield.